Hello.
Hello, ma'am.
Hello.
Good afternoon to all of you. I hope all of you must have had a very good lunch. And Sir is back with us. He has joined back with us. He will give us the session also. And we will continue till 4 at 4 o'clock. Dr. T.S. Ingole will join us from 6. So welcome, sir. Are you there, sir? Kuthe, sir, are
I'm
you
very
with us?
much on the line. Yeah,
Good
sure.
afternoon to you, sir. Thank you so much.
Yeah.
Your smile gives us energy, sir. Your smile gives us energy.
Oh, great, Anand. Thank you very much. But we'll be joining after lunch session. So it's a lot of responsibility on my shoulder to see that to keep the participant awake. That because they had a very nice lunch, hopefully, due to this festival season and all. So nice to share with you now my next slide on the yeah 1 minute. Just a minute. I'd like to share my slide now. Can you see my slide now? Can you see my slide?
Yes,
Roll up.
sir. Yes, sir. We can.
Yeah, great.
Yes, sir, we can.
Yeah. So now the next very interesting point about this 3D printing, especially the rapid prototyping, is that its usage in medical domain. Now this is really very interesting, and the doctors and engineers, they always say that they are professional friends, but hardly you'll find that they are interacting with each other. And maybe the doctors, they use the instrument and just for their purpose, and ultimately whenever they face any problem with the instrument, they only call the technicians and get it repaired and all that. And that is how the link between the doctors and the technicians or the technical people. But I would like to tell you that this particular 3D printing, which we call as additive manufacturing or rapid prototyping, this has actually changed the whole scenario in medical domain. And how exactly this is useful, I wish to rather discuss with you in much more detail. That I think this is where we are presently working on the VNIT Nagpur, and I'm going to show you the 3 institutes who are closely associated with our work on the 3D printing in medical domain. So VNIT Nagpur, IIT Bombay, and the DM Institute of Medical Sciences, which is actually near to Nagpur, Wardha. There is a place called Wardha near to Nagpur. And this DM Institute of Medical Sciences, we call it by short DMIMS. This is the medical college which is closely associated with our research work. And all these 3 institutes are closely working as far as the deployment of the research in medical domain is concerned of the 3D printing. Now, let me tell you that what exactly the research we are involved in, and top of it, as I already told you, like the deployment of the research. Now, when you are talking about the medical domain, the research deployment is only possible if you cure the patient. So ultimately, curing the patient is important. And for that matter, I would like to tell you that how we have rather entered in this domain, and ultimately how it has actually benefiting the patient and in general the people in the society. So this is the CAD/CAM center, as I told you in the morning also, that this is the project BETIC under the umbrella of this particular project, which is closely monitored by the IIT Bombay. So we are actually working on this project where we are using the 3D printing for the medical application. Now, I already told you about in the morning about the various instrument that we do have. And this is the rapid prototyping machine in VNIT, which we are using extensively. I'm also going to show you the another interesting machine, high-end research machine, which is used also in this medical application. But RP is the first machine where we have started working on this in the medical domain, and how the doctors are actually getting the advantage. So I'm just showing you in quickly the various areas where this RP machine is used. We also call it as layer manufacturing. If you look at this particular word, layer manufacturing is also word used for the additive manufacturing. So when you look at the engineering application, that means the green so-called arrows, it is all about the innovative design and manufacturing, pattern making, prototype or die design. So these are all the things which we are using in engineering application. And in medical application, you will find that we use it in medical mock surgery, that means medical model and mock surgery. And we use it in implant design. We use it in implant manufacturing. And we also use it in the high-end research arena, which you call as the tissue engineering. So I'm going to rather discuss on the other side of the application of the 3D printing, and that is related to the medical side. Now, I think when you talk about a healthy family, we must thank the doctor. It is because of the doctor we are always healthy, because he has always taken care of our health. But when you actually look at the some of the important implants that are used in the medical sciences to cure the patient, I'm just showing you an interesting figure where you'll find that there are standard implants which are used in the body of the patient. Many of you must be knowing that there is a hip stem or the femoral joint which is used. There is a knee joint, then there is a spinal implant, then there is a shoulder joint, then you will find that there are nuts, screws, everything being used. Now what you'll find that these are all made of metals. They're all made of metals. Shoulder joints and the spinal implant and the hip joint and the knee joint. They're all made of metal. Now, you know, as soon as the metal comes into the picture, then we raise our hand saying that, oh, it is my area. I'm supposed to know about that because it is made of metal. Had it been the living matter, the thing would have been, we would have kept ourselves aside. But when it is a metal, which is used to cure the patient, then naturally it is our area. And that is true. That is 100% true. That in orthopedic science, the metallic implant plays the dominant role. Out of these also, this femoral joint and the knee joint are very important. Why? Because the mobility of the person gets affected if these joints gets broken or if these joints gets damaged. So you know very well, if the knee joint is not proper, the people are not in a position to walk. Femoral joint, that is hip joint, is more problematic because if it is damaged or broken, you have to lay down on the bed, and ultimately this is what exactly you will always find, that the many patients, especially the older patient, they always face this problem that their femoral femoral joint gets damaged, and ultimately they have to lie on a bed for a longer period. So these are the implants where all this study has actually started. So I should say that whenever we talk about the vibrant or the moving family, then we must thank the orthopedic surgeon. And the research focus of the 3D printing
Sir, excuse me, sir.
is yes.
Sir, on the,
Yes.
sir, on the presentation that hide, sir, can remove, sir, that caption.
I should hide it. Yeah. Can you see now properly?
Thank you, sir. Thank you so much.
Yeah, sure. So you have to thank the orthopedic surgeon because he actually keeps us moving. As I already told you, our research focus is on the in the area of orthopedic sciences. As I already told you about the metallic implant that has been used in that. So how we have started using this particular 3D printing in the implant manufacturing, that is a key issue, or rather the key agenda. So I should say that orthopedic surgeon is a mechanical engineer when metallic implant is handled by him. And many times we used to say that orthopedic surgeon is our friend, and that's why we are closely associated with the orthopedic surgeon as a mechanical engineer. So let us look at some of the features of the manufacturing scenario in India. Now I told you about the metallic implant. I already told you in my last class that we are very poor in patent filing, and that is what you will find here also. Don't look at the other number, but if you look at the total patent filing in medical devices, they are very poor, not in thousands or even hundreds. It is because we are not actually manufacturing, or rather we are not inventing anything in the metallic implant. We straight away import it, fit it into the patient body, and ultimately we feel ourselves satisfied, which is the major problem. So there is a strong need of the metallic implant manufacturing in India. And as I already told you, the medical domain is one of the area where manufacturing is to be looked from a very critical point. What exactly I mean to say? You know, quality cannot be compromised in the product which is used in medical implant. Remember, implant, medical implant, whatever I'm talking about, it comes under the class 3 devices in medical devices. Class 3. Class 1 and class 2 are easy. Class 1 are very simple, like our thermometer and all. Class 2 devices are some of the rice tubes and all. But class 3 are the devices which are actually implanted into the patient body, and the product remains in the patient body. So medical implants are like that. So you have to be very careful, because if anything goes wrong with this particular product inside the body of the patient, this immediately the infection starts and there will be more complications. So quality cannot be compromised when you talk about the medical implant. And that's why the manufacturing of such implants, medical implant, is the key issue when medical domain is to be considered. And there you'll find that the 3D printing plays a dominant role. I already told you there is a stiff competition with the manufacturer from developed country. Exactly, I'm just repeating the same slide, that the implant that you get it from developed country is always acceptable to doctor, but the implant from Indian industry is always taken with a pinch of salt by the doctor. And therefore we have to compete with the quality of the implant that we get it from the developed country, and not only to only compete with this quality, but there has to be some innovation also in the implant so that it is sellable, and ultimately the doctors will also like to look into that innovation and start using it. Now look here, there is another very interesting issue, that whenever we focus our attention on the implant manufacturing, I'm going to discuss about it slowly. You know, there is another issue, like what are the surgical tools required for the implantation. I'm just showing you on the screen the some of the tools which are used while implanting the implant in the patient body. Now, all these tools are also imported. The imported implant is manufactured not only as a product but also along with the surgical tools. So doctors find it very easy that whenever he takes an implant, the surgical tools are also available, which actually helps in fixing that particular implant into the patient body, and therefore the uh, implant which is imported is always preferred by the medical doctor. But what is important here is to understand that when we are actually focusing our attention on the implant, we have to also focus our attention on the surgical tools. That means if we are designing and manufacturing the metallic implant, then we have to also look at the surgical tools, and that is one of the major area where we'll have to focus our attention on. Now, as I already told you, there is a tremendous confidence on the manufacturing developed country, and this is more problematic. That if there is stiff competition of manufacturing from developed countries, okay. But remember, it should not happen that as a small player in the medical implant, the big players will actually look at us and may actually grab us. That should not happen. So let us look at this in somewhat more detail. Now, about the medical devices, as I already told you that we'll be more focusing our attention on the implant. This is very disturbing. If you look at this particular slide, this is really very disturbing. Why? Because they say that the total global market is around 400 billion, and India is having the market of 40,000 crore in the medical devices per year, and it is growing 15% per year. The disturbing fact is over 80% devices are currently imported. This is dangerous. And you know, if 80% devices are imported, then there is a need of developing the import substitute devices in medical domain. Another disturbing fact is there are less than 300 companies with the GMP licenses. Less than 300. And out of that, 90% has a turnover of less than 50 crores. That means you'll find that there are very small number of companies who are entering into these medical devices. And as I already told you, when you talk about the class 1, class 2 and class 3 devices, then class 3 devices are important because the quality of that class 3 devices has to be the topmost. You will find that out of these 300 Indian companies, hardly any company gets fully involved in the class 3 devices, and therefore there is a need of entering into this domain. Again, I am repeating the same thing which I already told you in my last lecture, that there is a discomfort zone in the class 3 devices. Why? Because there is no compromise on the quality. So you have to enter into that particular zone of class 3 devices. And I'm really happy to tell you that at CAD/CAM Center, we are closely working on the class 3 devices. And our results are also very fantastic. But class 1 and class 2 devices, okay, a lot of people are working. They say that I am inventing a new thermometer, or I am inventing a new BP apparatus, or thermal screener and all that. That is fine. That is fine. But how many companies or how many research groups are involved in class 3 devices? That is more important. And we'll have to look into that. That's again repeating the same thing. All of us has to enter into that discomfort zone. So what is the point of concern? They enter in the market which is dominated by the imported standard implants. And number 2, implant which are not available on the shelf. Now this is interesting. Number point 2 is important. That is what we talk about, the customized implant. Now you know the standard implant of the I have already shown you in the one of the slides that various standard implants are fitted into the patient body. Say, for example, you are in a patient, suppose the implant is to be fitted. So naturally, patient may raise a question to doctor, sir, that particular implant that you are fitting into my body, whether it suits to my anatomy? You know, you will definitely accept or agree that everybody's anatomy is different. So if everybody's anatomy is different, how can you fix the same implant in all the human being. That means standard implant is available, which is manufactured in a lot, maybe as a mass production. How do you fit it in every patient as the anatomy is different? And yes, that is the important thing, and that is the point from where we have started our research. So what is important? Important is customized. It's the need of the hour. Look at these particular points. I have told you like anatomical variation. That means personalized metallic implant, cost factor, socioeconomic status, availability, rapid fabrication, reduced need for resurgery. So now here I'm showing you the so-called hip implants. Now every hip implant like this you need to rather design for the patient anatomy, and it needs to be manufactured also. What exactly we say when we talk about a customized implant? Yes, people of different origin and races. You can't think of the people in western side same as the people from the eastern side. Their races, origins are different, races are different. They are staying at a different geographical location also, and therefore their anatomy varies. You know, the person from northeastern side is definitely different than the person from the South Indian side. The anatomical size and build up varies a lot. Remember, it is mentioned, it is already proved that the Western and Asian counterparts are having a lot of differences, not only with the Asian population, but even they have proved to that extent that there is a difference in the gender also. That implant required for the human beings are different than the implants required for the men. So naturally, you will have to be more careful about it. Now, what exactly we have done research work at VNIT Nagpur? I think that will be of more interest to me, because you know whatever I had discussed up till now, this is just indicating you the need of the customized implant and ultimately the manufacturing of the metallic implant, because the implant manufacturing is the need of an hour. That's what we already discussed, and how we have started using this 3D printing. So let me show you that what exactly we have done. We have actually focused our attention on the hip implant. Now, hip implant is very important. I already told you that the joint which is very important in our body is the hip joint. Why? Because the hip joint gets broken, or if hip joint gets damaged, then you'll find that the mobility of the person gets affected. He cannot move. The people may ask, sir, with the knee and the hip, which is the most critical? I'll say hip joint is more critical. Knee, if it is not working, at least you can manage to move. But with the hip joint, you can't even move. You have to lie down. And many of you people must have even experienced that the aged people, as I already told you, when they actually, when their hip joint gets broken, most of the times you'll find that they lie in the bed, and many of them even did not survive. So what I would like to tell you, that this hip joint is important, and what we have done, that we have actually considered certain basic parameters while designing the hip joint. Now, various parameters like vertical offset, horizontal offset, anterior offset, neck angle, shape of femur, all these things we have discussed. So I will show you quickly what exactly this offset and all that. But what is important here, I think as an engineer, you'll find it more interesting about the angle, neck shaft angle. Okay. Now, this is the neck shaft angle which has been actually measured. So angle is very close to our heart, and whatever the implant is to be fitted into the patient body, suppose it is having a neck shaft angle of 120 degree. Now, when you have the 120 degree implant, you may ask the doctor, sir, whether the 120 degree fits into my body or something else. Because in engineering, we talk about not only the 120 degree or 121 degree, but we talk about even 120.98887 degree, like that. To such an perfection, we talk about the angle. So whether the neck shaft angle implant 120 fits into my anatomy, and whether the same thing fits in others' anatomy also, naturally the answer will be varying. We may say yes, it cannot fit into everybody's body. So naturally, everybody's neck shaft angle is different. And it may be even counter the way we talk about like 121.22, 130 point something like that. So what is important? That is standard implant, which is made with the fixed neck shaft angle, say for example 120, it cannot be fitted into all the patients. And that is why what is important here is that if we can manufacture the implant which is having the same neck shaft angle as fits to my body or my anatomy, that is what the surgeon wants. And surgeon always looks at you and they will say that, okay, then manufacture it. I'll be happy to implant the same thing into your body. So what we have done, actually, we have obtained the record of around 200 to 250 patients near to our area of work, that is central Nagpur, central India, and we have seen that if you look at this particular data analysis, that the vertical offset, I'll just take you back. This is the vertical offset we define it, a parameter. Now this parameter varies from patient to patient, and you can see that it varies from say around 20 mm to around 40 to 42 mm, and this is how the variation is. We have actually plotted it with the patient, actually taken the x-rays of the patient and looked into the vertical offset. Then we also plotted it with the horizontal offset. Again, I would like to just take you back to this horizontal offset here. This is what is the horizontal offset. And if you look at this, you'll find that yes, it is also varying. And as I already told you, look at the neck shaft angle. Oh, the graph is very wonderful because it is showing the variation of neck shaft angle in the area which I have considered only the central India, that means Nagpur and nearby Nagpur. You'll find that it varies from 124 degrees to 140 degrees. So where exactly my neck shaft angle fits in this particular graph, that is interesting. And if I can manufacture that implant having the same neck shaft angle as required by the anatomy, I think I'm on the right path. So what exactly we have done? We have used rapid. That means the 3D printing extensively to show the feasibility of process of manufacturing the implant, having the same parameter as required by the patient, and that is what we talk about a customized implant. I already shown you this particular figure. Again, just a repetition that you have your CAD file ready. You can convert it into the STL file and your product is ready. That means you can get the physical product directly. Can we use this rapid prototyping in medical domain? Answer is yes. Look at this picture. Very interesting picture. Now, here you'll find that I'm showing you the CT scan machine. This is a CT scan machine. Now, if you rather take the file from the CT scan machine, they call it as a DICOM file. If you take that DICOM file, you can straight away feed it into the RP machine, the same file, and you'll find that you can get a physical model of medical organ, that is a bone. Now you can see here the bone. I can get this particular bone directly from the CT scan of the patient. Now I can use this as the pattern, use hopefully the casting or machining, any manufacturing process, and it will be possible for me to get the metallic implant. Now I have actually shown you here the 0.5 scale of the femur bone, which we have casted in VNIT using this particular technique. So this is actual figure of the implant, that means the metallic implant, which we have done it using the casting. Now here you will find that this implant manufacturing process is a wonderful process using RP. Why? Because here if you look at this particular figure, you will find that this particular product that we get it directly from the RP is used as a pattern. And we have actually set up the whole procedure and executed a project which is called titled as Development and Testing of Customized Joint Replacement Implant using layer manufacturing. Now look at this particular cycle. This is actually the project that we have completed from 2009 to 2014, and I would like to just tell you quickly this particular project in a form of a cycle. We don't want this cycle to be complete. Why? Because this cycle shows the healthy individual, either he meets with an accident or he becomes a patient because he has not eaten the food. So now, once anybody breaks his joint, maybe in an accident or becoming a patient, then you get a CT scan of the patient, get the computer data, and get the medical imaging. And using this medical imaging, you can get the CAD data. Now, this is a really wonderful steps in the medical domain where the engineers are used extensively. Because once you have your DICOM file from the CT scan machine, you have to convert that into the CAD file, which can be straight away given to the machine called rapid prototyping machine, so that you can get actually the product. Now here, this is being used using the software called Mimics, and we have the Mimics software where our students have, my research students have actually designed the implant, and these implants which are designed patient specific. Using this CAD data, you can get a metallic, you can get the pattern which can be used for the casting. And here we are also using the casting simulation software, as I already told you in my last lecture of Smart Foundry, that the simulation software actually gives you the complete data that what should be the parameter, you should fix it in the casting. What should be pouring rate, what should be the molten metal temperature, when the ambient temperature varies, what you should do, and all that. Even it gives you the cost also beforehand. And with this, whatever the product you get it, that will become a zero defect product. Then you can use this particular implant which is manufactured, test it, and use it in surgery, and make the patient as a healthy individual again. So this is what is a complete project that we have handled. We have shown the feasibility of this particular process, and I am happy to share with you quickly after this that we have actually, or rather we have executed some live cases in patient in the DM Institute of Medical Sciences and the SIMS Hospital in Nagpur, where we have actually implanted the metallic implant into the patient body. So if you look at this particular project, it's the design of the implant, then the manufacturing of the implant, and the testing of the implant, and then fitting it into the patient body. Okay. Now let me show you quickly some of the very interesting case studies that we have executed. I already told you that doing something actually proves, or rather that gives the credentials to the research. Otherwise, many times it happens that whenever we interact with the researchers, we always ask the question to the researcher, how many papers you have published? And maybe he can tell you the numbers the way he likes or whatever it is. And then there again, we then go on cross questioning that, like how many, what is the impact factor, and whether it is an essay, a journal paper, and all that. You know, it's one way of rather evaluating how best you have done the research. But the other interesting part is in the research is that you should ask the researcher whether you have patented your research or not. And if you have patented the research, whether the product or the process that you have patented is in actual use for the benefit of the society, for the people in the society, then only our research carries the importance. Let me show you one of the very interesting case studies here. This is actually the 3D city. This is actually the TMJ joint. They call it as a temporomandibular joint. Now, don't worry about the very big name in medical sciences. Initially, you feel somewhat disturbed, but later on, you know, with more and more use, nowadays I don't feel it because I'm using it quite extensively. So, temporomandibular joint. This is for the bony ankylosis. This is actually the case of a girl who met with an accident, uh, around 6 years, and her joint got broken. This is actually the joint of the mouth near the mandible, and because her joint got broken, therefore she fused, and therefore it was not possible for her to eat any solid food. So she was on liquid diet, and ultimately she was required to rather go for an operation wherein the implant is to be fitted into the joint to overcome this bony ankylosis. You know, let me show you what exactly this particular picture talks about. The doctor approached me saying that, okay, Professor Kuthe, we would like to design the joint, which is for this particular lady, and she is having this problem, and we need to manufacture a metallic implant which can be fitted into her body. Now, you know, when he actually approached me, I was rather more worried, like how exactly the part is to be manufactured. So I asked the doctor, why don't you draw the figure of the joint so that I will be in a position to understand, because I'm more interested in manufacturing part of it. So, you know, doctors is actually drawing something on a paper, a drawing. It's really very difficult to imagine. With due excuse to the doctors, we can't even understand the letters written by the doctors or the any words written by the doctors. And when I'm asking him to draw something, and that too the drawing required for the engineering part manufacturing, you know, I was helpless, and our interaction was not very fruitful. So then what I have done, I told him that why don't you actually get the things through the clay models. And what he has done, I have given him the clay, which is generally used by these children to play. And I told him, okay, draw what, rather make the model so that I will understand how best this particular part can be manufactured. So that is why I'm just showing you the clay models here. He has drawn the clay models like this. I have reverse engineered that, got the CAD file of it. Then using that CAD file, I have actually got this 3D printed joint, and we actually tested it for like whether it is properly operating it or not. So it was a nice interaction with the doctor. He is the person who is in need of the product, engineer as a manufacturer and the designer. So our fruitful interaction has led to this particular uh, uh, development of the implant. And now you can see here, this is what exactly the joint before the implant fitting. This is how he has actually asked me to develop the joint, which we have made it as per the doctor's suggestion, and this is fitted into the patient body. Sorry for the blood and everything being shown here, but anyhow, this is how we are fitted into the patient body. And you will find that the girl, she was not in a position to open her mouth for the last 6 years. Now with this joint, it was possible for us to open the mouth, and you know, that was something great. We achievement that we have actually enjoyed. I have also published a paper on this in Rapid Prototyping Journal, volume 17, number 5, 2011. You can go and see the paper. But let me tell you a very interesting thing here, that when this particular case study was performed, you know, the doctor, he was so excited. He said, Professor Kuthe, I would like to arrange the press conference for this. I said, okay, if you are happy. And then, you know, the first time I seen in press conference, how to get the press conference successful. If you can arrange a very nice refreshment to all press people, they will be very happy to see it in first glance. Okay, they are taking care of our hospitality. Anyhow, so let's joke apart. So that refreshment, in that refreshment, there was samosa. And this girl, she has not eaten that samosa for the last 6 years. She was looking at that samosa. And when she was looking at that, then the doctor asked her whether you would like to eat that. And she said, yes, I wish to eat that samosa. When she has taken the first bite of samosa, the satisfaction I have seen in her eyes, I have never enjoyed that satisfaction in my life. But even after getting the PhD degree, or even after getting the promotion, or even developing any mathematical model or anything. So such satisfaction in the common man, I think, is the deliverable of the research that we have done. So this was a wonderful case study. I wish to tell you another one. It is about a metatarsophallangea joint implant that we have fitted into the patient body. Now this is also again another wonderful case study. I think you can go and refer our rapid prototyping journal paper, volume 20, number 4, page 270 to 279. I think very year I have forgotten, 2013 somewhere. So I think with volume and number 4 you will get that. So this is about the joint implant that we have fitted into the patient body, and I think you can see here. This is what is the metatarsophallangea joint. Now this particular implant, which we have designed using the X-ray, remember, using the X-ray and then rapid prototyping, that we have taken the all dimensions from the X-rays, developed the CAD model, got the rapid prototyping model, tested it properly, and then got the metallic implant. Even we have carried out the analysis using the ANSYS software, so that the stress subjected to that particular implant is well looked into. And finally, this is the operation. This is actually the surgery that doctor has done, and you can see here that these are the post operation results. So it's a, after the operation, we have taken the feedback of this patient for the 2 years continuously, and we found this particular joint very successfully working on. Again, let me tell you one very interesting thing about this particular patient. When he got married later on, during the reception, he told his wife, I can dance today in my the marriage only because of Professor Kuthe and the doctor. So, because he was so comfortable with this particular joint, which was rather problematic for him when the K wires were used. But this is what is one of the interesting case studies. I think you can go through the paper and see what exactly, or rather how various steps that we have followed. Now, this is another very interesting case study. Design and development of implant for mandible affected by the malignant tumor. This is actually the case study of a woman who has actually suffered the tumor in the mandible. Now you can see here, this is the actual RP model that we got it, where you can see this is the tumor. Now this tumor, which is in the mandible, generally in case of such tumor, the very first option is to go for the surgery and remove that tumor. And then they follow the chemotherapy and the radio therapy later on. But then actually you remove such tumor here, then there is a wide gap in the mandible, and there will be a deformity in the face. So what we have done, we have again followed the same methodology, the way I already told you in case of the temporomandibular joint. We have actually developed this particular implant the same way, the clay model and all that, then the RP model, the way you look at it, and the metallic implant, as you can see, and actually surgery that we have fitted into the patient body. And you can see the face of the woman with the tumor, and now face of the patient without with our implant which you have designed, and you can see that the deformity in the face is right. So this is one of the wonderful application of the development of the implant for the mandibular. So cancer patients, they are benefited a lot, and they can be benefited a lot if you use the 3D printing in case of the design and development of customized implant. Remember, we are only talking about the customized implant. That means the implant which are required by which is suiting to that particular patient. Now, about this particular case, I would also like to tell you, one of my researchers, he has developed a wonderful application that is called as a surgical guide. You know, when just to take you back, whenever this particular implant is to be resected and the implant is to be fitted, the doctor should be given total flexibility from where exactly the part is to be cut and all that. So my researchers has actually developed this particular surgical guide. You can see here this slot. So this particular slot is ready, and what doctor has to do, he has to take the scalpel, that is what they call it as a knife, and just put it in that slot, cut it this way, and once you cut that, you can see here, you can cut it from here, the tumor will be removed, and you can fit the implant exactly here on this particular joint, so that the complete surgery is possible with minimum time. So he has worked on the customized surgical guide for the customized implant placement, and I'm happy to tell you that this researcher who has actually completed, who has finished his PhD in customized surgical guide, he has presented this particular work to the government of India, and through the BIRAC big grant, he got 50 lakhs to start his own company, and his company is already in operation in our incubation center at VNIT Nagpur, and his company called PCSearch.co.in is operating, and you can interact with him. You can see that how best he is in a position to provide such solutions to many doctors in India. So that's one of the interesting thing. He has done a lot of work on this. So now let me tell you, to rather take you to the another interesting area called tissue engineering. Now, as I already told you, implant manufacturing is possible by using the 3D printing. But whatever we are talking about is all about the metals. And you know, metals are inserted in our body. Remember, I think all of us are experiencing after we have taken after the lunch or the dinner, if some food particle gets stuck in our teeth, our brain is disturbed, and brain continuously picks up saying that remove that food particle. And we actually work in such a way that we take our tongue there to remove it, or maybe then we are forced to take the toothpick and then remove it and all that. So the brain indicating that there is a foreign material, we don't want that material to be there. So here, think of the metal being used as a class 3 device inside the body of the patient. The brain is unable to understand what to do. So what is the solution? Remember, it is not about the metal, but remember, the brain gets disturbed, and there are always the problem with the metal implant. As there is no solution to the metal, therefore we are using it, but in long run it may lead to some problem called metallosis. Sometimes they also call it as the stress shielding. And in medical literature, it is emphasized that in case of orthopedic sciences, bone should be replaced by bone, organ should be replaced by the same organ. So you are replacing bone by the metal. That is not at all acceptable in medical literature. Though we don't have any other alternative, therefore metal is used as a gold standard. But ultimately, you have to replace bone by the bone. So can we think of getting the implant made of bone? The answer to this is yes. The tissue engineering is the new area, which is now developing very fast, and we are doing a lot of work on that. Let me show you what exactly we are doing on the tissue engineering. You look at this particular figure, you'll find that whenever there is a major so-called defect, so this is a major defect, here we actually put a scaffold. Scaffold is nothing but, you may call it as a meshy work. That means a mesh. And in this mesh, we allow the cells to develop. So that is what they talk about the tissue engineering. So if you look at here, what we do, we make a ceramic scaffold. That means a meshy, the ceramic material is a biocompatible material which is accepted by the body. And in this ceramic scaffold, you, or maybe in the polymer matrix, which is again acceptable by the body. Implant these cells and some bioactive molecules to which they call it the growth factor, and you'll find that slowly in this particular so-called pores, the cells will start growing, and here you'll find that instead of metal being put in this area, if you can put a scaffold, you'll find that the bony structure will start developing, where the ceramic is the scaffold material. So can we think of the material which will degrade in long term, and then also the cells will start building and the whole thing will develop as a bone? Answer is yes. That is where the research is in the process. So here you'll find that the tissue engineering works wonderfully. Let me tell you what exactly we are doing in bone tissue engineering at VNIT. That's what we have already the well-established tissue engineering lab in CAD/CAM center. And again, the same cycle where I don't want again these cycles to be completed. Why? Because I don't want a healthy individual to meet with an accident or to become a patient. But again, see here that the patient CT scan is now thoroughly studied. That is using the medical imaging. And then we actually manufacture this scaffold in the 3D plotter. So we have this particular instrument called 3D bioplotter, where we actually make the scaffold which is suiting to the patient's body. Does you mean to say it is a customized scaffold? Answer is yes. It is a customized scaffold, and this scaffold, in this scaffold, we seed the bone generating stem cells, where we have the biosafety cabinet, we have the CO2 incubator, where we actually see how the seeded scaffold is getting developed. Through the inverted microscope, we look at the various how the stem cells are developing, and then we test it. Finally, using the surgery, the scaffold is fitted into the patient body. But this is all the proposed thing that we are looking at. But what is important here is that the stem cells plays the dominant role. That you have to get the stem cells either through the bone marrow and put it in the ultra low temperature freezer, and then put it in the then seed it in the scaffold. But these stem cells always poses a problem, especially from the ethical committee approval or maybe from the patient consent. Now we have entered into another area of the bone tissue engineering, where we actually fabricate the scaffold, and that is what is the first thing that we are talking about as far as the mandible scaffold is concerned. In case of cancer patient, we manufacture the scaffold suiting to the patient anatomy, and we simply put it into the patient body, and you'll find that the patient body itself takes care of putting the stem cell through the blood and ultimately developing the bone tissue in the scaffold. This is what we are presently working on. Around 10 to 15 live cases we have already completed in DM Institute of Medical Sciences. And we find that it's a wonderful alternative to the stem cells work in the bone tissue engineering. So this is actually the 3D bioplotter, a wonderful instrument that we do have. We have worked extensively on this, and we are happy to share with you that around 15 cases when we have completed, we found it very interesting, and many papers we have published. Around 2 students have published, has completed the PhD, and Professor Vikramjit Basu of ISC Bangalore, he has appreciated our work. He is also one of the pioneers in tissue engineering. But that is what is one of the area where you'll find that the 3D printing is playing very, very important role. So this is one of the interesting point I would like to also talk to you. The scaffold is being prepared with the different orientation using the bioplotter, and we can even think of that which is the best orientation for the fast cell development and the tissue regeneration. And these are the various structure that we have discussed about. So bioprinter scaffold for fast osteointegration, That is what is the new area where we are presently working. He is Dr. Pranav, who is my postdoctoral fellow working in tissue engineering lab. These all things we are doing under the project called BETIC. I already told you, Biomedical Engineering and Technology Incubation Center, which is a project where the IIT Bombay is the lead center and VNIT Nagpur and CVP Pune are the satellite center, which is having a financial outlay of 39.39 crores. Here, what you'll find that this picture indicates very nicely doctor demanding the instrument, doctor demanding the medical device, and engineer is ready to supply. That is what we do want. So ultimately, that is how at VNIT we are working on. Let me tell you, we call this by the nickname called BETIC. And this BETIC as an R&D project, all of you can just go through the Google search and you will find out our website of BETIC. You will find it quite interesting to look into that particular website and enjoy what we people are doing. Here, this we call as an R&D project. That means here D is bigger than the R. That is what I told you. Research papers, even if we are less, doesn't matter. But whether the deployment of the project is happening or not, that is what we look at. And that is what I told you, that our success of the our success of this particular research in the deployment of the implant in the patient is more important to us, and that is what we are presently working on. So this is all our medical device innovation ecosystem. We work with the people under the three process. We start from the doctor first, develop the product using the researcher. We go to the entrepreneur and ultimately see that the part is fixed into the patient body. As what I told you, that two of my researchers have successfully incubated the company. Third person is in the line, and these three companies are actually the companies that we will be incubating and delivering, or rather deploying the research in the society. So this is what is the 9 medical products, even more than that now. This is the 2015-16 data I'm showing you. Now we have almost done more than 30 products, and this is our map of the BETIC, where we are using, we are working on not only the hospitals, but with the government, with the industry, with the academic institute, and you will find that all of them are together. And remember, it is a translational R&D for the medical device innovation. So it is a define. This is what we say: define, develop, deliver, and deploy. So you know again that particular values of death I have showed to you. Exactly here also we have to see that whatever we are defining, whatever the device we are developing as an innovative, it should be developed. It should be possible for us to see the entrepreneur who can manufacture it, or rather you yourself start your own manufacturing company and then see that it is deployed in the patient. That is what and ultimately it is not a deployment in the patient, but the gaining the confidence of the doctor in the product which we have developed. So finally, before I conclude, let me tell you quickly, the product design plays the dominant role in the medical device application. Product design talks about this is the same thing which I have already told you about. So here the translation from idea to the market is more important. And this is what you can see here quickly, the across values of death, how the values are from product to the market. That is the same thing as I already told you. That this is very interesting and we have to focus more on this. I told you, like if you don't find a company, run your own company and see that the product is deployed, it is accepted by the customer. So right from concept to the market, it's a big task. As an academician or as a student, you have to take and see that you are successful. Ultimately, as I already told you, it is to gain the confidence of the doctor, and not only that, the figure I told you, 80% devices are imported. That should be that we need to overcome fast, and we have to see that the import substitute products are possible. So this is what we first I sometimes feel. We look at this figure 60, 30, 10. We feel that the research, the idea, engineering is 60% and the rest are very simple. But actually it is opposite. It is only 10% effort there. 60% is towards the market. See that the customer is happy with your product. So all these things are very interesting. And again, I hope through the various methodology we are executing it. I'm requesting all of you again to do, or rather, I'm inviting all of you to visit our CAD CAM center, see how we have done it, how we are trying our best to rather get these things executed. And if you get encouraged and start your own company, I think we are successful. That is what we always look at. So this is the product design. Quickly, I would like to tell you that the bionics plays the important role in product design. Whenever you have to develop any concept, see that look at the nature and you will find that the concept is with you. The burr, the Velcro is designed by using the burr. To the well shape, the turbine blades are designed. Shark skin helps to develop the swimsuit. Termite dam has actually helped us to get the office building. So ultimately, research to be sellable, technology and science should go hand in hand. So that is what they always say. The major contribution of country must be engineer and scientist and not the accountant and economist who just create the services. I don't mean to say they are not important, but important is that it is the engineers and the doctors who will be important. Let me show you this particular figure. Now, this is the bullet train which I have seen in Japan during my visit to Nagpur University. Now, I would like to just tell you about this particular engine of the bullet train. Bullet train runs at a speed of 103, 150 kilometers per hour. Even now, they are thinking of taking it higher to that. Now, when it actually designed, you know, the train, when it was actually coming out of the tunnel, it was creating a lot of noise. Now, when it creates lot of like boom, sonic boom, so it was disturbing to the people, those who are living in the Japan. And you know, the Japanese people are very sensitive to this noise. So they found that this is a very problematic. So ultimately, what the design engineer thought about how to overcome this problem. Luckily, he was a bird watcher, and when he has seen the kingfisher dashing from the air to the water, picking up the fish, and again going back, he found that there is hardly any noise. So he looked at his beak, and then he found that the whole design of beak is responsible for not making a noise. So he has changed the design of the engine of the bullet train, matching or mimicking the beak of the kingfisher, and you know the problem is solved. So this is what exactly the product design talks about. Why I had told you about this product design, because in medical devices, especially in case of the customized implant, the product design plays the important role. I think you have already seen it when I had discussed with the doctor, and then got the clay model and then changes the design and all that, and then we fitted it to the patient. Exactly, there you will find that this is all interesting. So conclusion is, make in India for medical implant. This is important. Then there has to be strong academic linkages of all the institute for sharing the human and material resources. Everybody has to be there. Not only the ISC, IITs or NITs, all engineering institutes should be together. And the innovation, the way we do it in Betic model, the need starts from the bed. That means you look at the patient and you will come to know the need of the device, which the doctors will tell you. On the bench, develop the product. And again, take it to the bed. That means put it into the patient. See that the patient is comfortable, patient is treated. So this is in general what we have done in the Betic model using the 3D printing. So thank you very much for the patience hearing, and I hope I'll be happy to interact with you through the sharing. So thank you very much. I think can I
Wonderful, wonderful presentation. More than what I thought you would give.
yeah, thank you, madam. Thank you very much.
I believe
So let me check, madam, whether there is anything on the chat so that I can answer the questions if at all the students are.
You on the
Yeah.
microphone, they can, sir.
There is something on the chat like materials for hip joint process being a mechanical engineer role. What property we should? 1 minute. We should check and consider. Yes, very nice question by the Subhash. You know, whenever you talk about the hip joint processes, the one of the major critical property is the wear of the implant. So resistance to the wear is one of the major property that you have to look into, and that is why till today only three materials are only considered to be the best as far as the biocompatibility is concerned in case of hip joint. That is, they talk about the stainless steel 316L, they talk about the cobalt chrome alloy, and third one is the titanium alloy. So these are the only three materials still today they are used in hip joint prosthesis. The work on the magnesium is in the process, but this is what exactly we are using in case of hip joint. Yeah. Any other question? Yeah. Any question? Let me. If anybody is having question, I'll be happy because more interaction naturally will help me in.
Dr. Piyush Jain, if you can hear me, you can ask your question yourself, please. Dr. Piyush Jain.
Sir, there is one question.
Yeah.
Hello.
Yes,
sir,
yes.
that density of the metal, suppose stainless steel density of that metal, it is more than the maximum bond. So any other material, suppose composite, biocomposites, can be replaced with stainless steel for implant?
Yeah. What you said is absolutely right. That there is always a problem of matching the bone and the metallic implant. Now think of a metallic implant fitted into the bone. Naturally, there is always a problem that the density of, say, for example, stainless steel 316L, if I talk about, now it is definitely a metal, denser metal, and your bone is that way porous, having less capacity. So you will find that there the mismatch is always there. So that is the osteointegration, that is what we talk about, and therefore titanium is more preferred. But because it is costly, the people still uses the stainless steel in developing countries like India. But this always leads to a problem which is called as a stress shielding. Because we are talking about an implant called hip implant, the load bearing implant, you will find that the load get transmitted through the metal implant, and then bone remains without any transmission of load. You know, this is the peculiar feature of our body. If any organ is not used, then the body makes that particular organ inactive. Exactly this thing happens when you use the metallic implant, and such phenomena is called as stress shielding. We have to avoid that, and for that, as I already told you, tissue engineering is the right solution. And we are also working hard to see that this tissue engineering leads to in vitro organ development, which will serve as a substitute for the organ transplantation in the long run. So yes, that is true. Yeah.
Thank you, sir.
Yeah.
Sir, so your presence, someone has written, sir, your presentation was highly impressive and motivating. Thanks for the same. And more information. Sir, pranam for your contribution towards the society, engineering, and country.
Yeah.
Products, sir. One question: what is the
What
age of
is
3D?
the age of 3D printed product? You know, I don't understand. By the age, you mean to the sustainable? That means how far it will remain in the body without failure. That is what you mean to say, Chaurasia? If that is the case, I think you know, the class 3 products are always having certain life. you can't say that I have put the metallic implant into my body, so it will remain forever. There is certain age, or that is what we don't call it as the age, but the life of that particular product. Generally, the if the implant is fitted into the person who is aged, then there is no issue, because we ask him to slow down his activity so that there will not be any problem, and it remains lifelong till his death. But when you actually look at the young patient, I think yes, in such scenario, we had to be very careful when you are using the 3D printed product, because the titanium, if you can use the 3D printed product, then you will find that its life is more compared to the stainless steel, compared to the cobalt chrome alloy. So it has the better life. And again, I'm repeating the same thing. That is where we are more interested in, that if we are successful in tissue engineering, then the 3D printed tissue engineered product will have the more life, and you can, once it is fitted, it will remain fitted forever, and there is no need of, they call it as a revision surgery, because revision surgery is also a very problematic thing. So there will not be any revision surgery. Now, one fellow has asked, what is the cost of the implant? That is what it seems. Yeah, you know, if you ask the cost, I think that is what exactly we wish to enter into that particular domain. I told you in my last lecture, the low cost, there may be some problem with the quality. High cost, there will not be any problem with the quality. I think if you are talking about the medical implant, 3D print, medical domain, I think quality is not at all compromised. And therefore, even if it is costly, doesn't matter. The doctor will be ready to use it. He can even convince the patient that, yes, this is the best product, so better pay for it. And that is what the cost of metal product is important. I think he has also asked what is the cost of metal 3D printer. Yeah, metal 3D printer is very costly. It goes in crores. But I think the day is not far off when you find that within the 5 or 6 years, the cost will come down. Yeah, anything else? Yeah, one fellow has asked how to bring cost of this product less so that last person of society should also take its benefit. Yeah, as I already told you, like if you can develop an innovative product, focusing more on the process, and that to manufacture at your local industry, hopefully the cost will be less. I already told you, imported implants are costly, because the people, the industries in the developed country, they know there is no substitute to their product. And you know, that is what I have even experienced many times in the with the people of high repute. They say that just tell them that you are developing the product. Immediately they will bring down their price without even understanding like what you are doing. So you know, if you show your willingness to manufacture the product, maybe by the knowledge that we have gained through our lecture of Industry 4.0 or whatever it is, I think the day is not far off when you'll find that the cost of the implant is affordable to anybody. There is another question like, what is the difference between the product made by 3D printing and product made by metal powder? Metal powder is used in 3D printing. That is what the process of SLS that we use it, and metal powder is used. But there is another one called a powder metallurgy, where you actually compact it by the pressure. So such thing is not considered in the 3D printing. It is actually layer by layer. If I'm not wrong, 3D printing starting material is powder form, and you mentioned it is stainless steel. What about? Oh, sorry. You know, there are various 3D printing processes. The best way is to classify them into the three categories. One is the solid based 3D printing, liquid based 3D printing, and powder based 3D printing. Whatever I talked about is the solid based one, that is using the FDM technique of 3D printing, where we get the solid model in the ABS plastic, and we use it as a pattern to get the stainless steel one. So it is a rapid prototyping assisted conventional manufacturing that we talk about. So I'm really happy that there are so many questions, and hopefully answered everything. I'm really surprised that Vandana madam has put the next lecture 4 o'clock again. The participants should be ready to digest another very good lecture by my colleague. He was my student, very first student who got a PhD under me, and I know his lectures will be wonderful for you to hear. So I'm really glad to interact with you people all. So anything else from my side, I'll be happy to interact. Yeah.
Samosa eating by girl was heart
Oh, samosa eating by girl was a heart touching. Yes, madam. Even that day in the press conference, the tears rolled in my eyes when I have seen that girl was eating the samosa. Never you get such an experience anytime in our engineering curriculum, in our engineering career. Yeah.
So please sharing about one suggestion.
Yeah.
Engineering is so skilled and so practical. Then
I'm not hearing you properly. Can you just yeah.
When engineering is so skilled and so means practicable, then there should be some courses of 1 year or 2 years in which the persons can be skilled with such type of implant engineering and this another type of skills.
Yeah.
Suggestion.
Yeah, that's true. That's true. We have actually, I'm trying my best to see that. But there is one very good course run at IIT Bombay. They call it as M.Tech Biomedical Engineering, where the engineers and doctors are actually sitting together to learn about the biomedical engineering. Another course, I think, hopefully IIT Hyderabad is also offering, and I'm also trying my best to offer such course in VNIT Nagpur. But only time will tell when it will be possible. Yes, but such thing is very much required, and I think engineers and doctors will work together for the benefit of the society through such initiative. Yeah.
Thank you, sir.
Yeah.
Sir, I'm so
Hello?
glad to see that even after lunch, all the participants are still so curious and still asking questions. One more question, I think. One more
Hello,
question.
ma'am.
Yes, sir. Yes, sir. Please carry on, sir.
Okay. Thank you, ma'am. Good afternoon, sir.
Yeah.
Sir, I have one question. Is there any tools and techniques is there to predict the lifespan of the developed material?
Lifespan of developed material. You mean to say the implant that we fit into the patient body? What is the life of that? Yes. Frankly speaking, this is a very critical issue because everybody's chemistry is different. The implant is subjected to so many chemicals. Implant is subjected to the live organs. That means the non-living substances with the living substance. And in such scenario, it is really very difficult. And that's why, we talk about the biocompatible material. Sometimes we talk about the bio-inert material like ceramic. But we are not in a position to develop a new material which is proved, which is competing with this. And that's why we say that the success in tissue engineering is the key today for the research in biomedical engineering. So we are trying our best. Even we are submitting the proposal to various agencies where we are interested in getting the confidence of the doctor by using the fabrication technique which is assisted by the artificial intelligence. So such type of the projects are also in the line, and so because ultimately we have to win the confidence of the doctor. Doctor is, or the surgeon is, the key so-called actor. If he is not ready to put your implant developed by you, fabricated by you into the patient, nothing has happened. So such thing is definitely is the key issue, and hopefully the success in the replacing bone by the bone, replacing liver by the another liver which is developed in the lab, that is what is the future. That is what is important.
Okay. Yes. Sir, I have one more question.
Yes.
How will you identify that bio-friendly material from among n number of materials?
There is nothing like an identification. As I already told you, some of the materials have been already proved, but there are certain tests that is carried out. So various tests are carried out, mechanical tests, biological tests, cytotoxicity and all that. These are the already well mentioned in the protocol. If you can follow that protocol and get that test done, there are agencies available outside. They will give you all the test. They will actually carry out the test for you, and based on their result, you can say that that particular material is biocompatible or not.
Okay. So suppose we identified some material for implantation. What are all the competent authority we have to get the approval for implantation?
Yeah, there is the FDA approval is required from the government of India, from the government, and ultimately, you know, for that various labs are already there in India who will actually give you the permission to use that particular material. Now Professor Bhatnagar is working on the magnesium at IIT Delhi. So such type of things are slowly coming up. But remember, developing a material for any purpose in the body as a class 3 device definitely is the ocean as far as the research is concerned, and lot of work is required to be done.
Thank you, sir.
Yes. Nice. So I'm really happy to see that one fellow has written that the samosa story might have got tears in many eyes for sure. Oh, I'm sorry. Thank you. I think practical oriented sessions like Sergey will never be exhaustive, will always be energizing. Thank you so much. Oh, great. So I think, madam, if no other question, I think I should rather keep you free for the next lecture then.
Thank you, sir. Thank you so much. As you could see from the questions which came up, that even after having lunch, nobody took a nap also. So, sir,
I'm happy that the students are responded so nicely. Yeah.
Sir, it's very difficult to hold the students for 1.5 hours, that too after lunch. We are your students only, sir. So
thank you, madam.
So much, sir. It was a pleasure listening to you for the first time, but not the last time, sir.
Oh, I'll be always with you, madam. Anytime, just call me.
Hope to listen to you more and more, sir. Thank you very much, sir.
Yes, sir. Thank you, madam. Thank you.
And for all the participants, sir is about to join. Maybe 2-4 minutes more left. So we'll be back. We are not leaving the session. We will not leave the session. Sir will be back.
Yeah. So, madam, thanks to you. So I'll be leaving the meeting. Okay.
Thank you, sir. Thank you. Thank you so much.
Thank you. Thank you.
Good afternoon, sir. Could you join, sir? Sir, I'm sending you invite. I'm sending you, sir. I'm sending you invite. If you can get, please tell me. Just hold on. I have sent send you invite, sir. Could you get it? Could you just accept it, sir? Sir, it will take some time. Wait a minute, sir. Till the time. Yes, you've joined, sir, but I cannot see you. Please open your camera. I cannot even hear you, sir. Okay, but we are not able to see you, sir. Unmuted, sir. Abhi, I cannot hear your voice. Maybe after 2-3 minutes, because network issues are there. Yes, I can hear you, sir. I can hear you now from your microphone. Sir, we still have 2 minutes.
Hello.
Yes, sir. Good morning, sir. We still have 2 minutes. By that time, kindly give me permission to read out your resume to them, sir.
Please,
Please.
can you see video also?
Just a minute, sir. Just a minute, sir. Yes, sir. I can see you, sir.
Okay,
I can
fine.
see you, sir.
Okay, so shall I share this desktop?
Sure, sir. Sure, sir.
Okay.
Just now, Professor A.M.Kuthe introduced you that you were his first PhD student. And
Yeah.
sir, we are so happy that you are with us. And
Okay.
sir will be telling us about rapid tooling. Am I right,
Yeah.
sir?
Yes, sure.
Thank you so much, sir. It's visible, sir.
Is it visible?
Yes, sir.
Okay, fine. Now you can continue and just tell me when I should start.
Yes,
I'm
sir.
ready now. Okay, fine.
Just a minute, sir. Just a minute.
Sure.
So once again, a very warm welcome to all the participants and a very good afternoon to Professor D.S. Ingole, sir. He's a professor and head of mechanical department at RMITR Badnera. He has 27 years of teaching experience and 2 years of industrial experience. His area of interest include CAD/CAM, robotics, and rapid prototyping. He has to his credit 17 national and 28 international papers that have been published. Subjects being taught by Sir is control system engineering, industrial management and costing, measurement system, CAD/CAM, robotics, robot application, and SIM. May I now ask Sir to please continue with the session. Thank you so much, Sir.
Thank you, madam. Hello, friends, everybody.
Pleasure was mine, Sir. Please continue.
Yeah. Is the voice audible enough?
Yes, sir. It's audible to me. How about others? If anybody can speak up.
Yes, it's audible.
Audible, sir. Audible.
Fine.
Thank
Audible,
you.
ma'am.
Thank you.
Audible, sir. Audible.
Thank you, sir.
Sure. Thank you. So, everybody, good afternoon. So, I welcome participants also. So, my sincere thanks to Dr. Vandana Arora, Head of Mechanical Engineering Department, Gyanganga Institute of Technology, Jabalpur,
Sir,
for
please presentation.
giving. Yes, anybody wants to speak?
Please keep in presentation mode, sir.
So, for giving me opportunity to become the part of this faculty development program on advancement in manufacturing technologies for industrial applications.
Chandan, sir. Chandan, sir, will you please mute your mic, please? Chandan, sir, please. It's a request. So sorry for the disturbance. Please continue.
Thank you. So, we'll continue.
Yes, sir.
Prototyping is the essential part of this product development process, and prototyping has many applications as far as industrial applications are concerned, just like the concept modeling, functional testing, checking the form fit and functionality features. It is also a lot of applications in medical sciences, and the participants are listening lectures on this rapid prototyping, I hope, since last 2 or 3 days. And today you listen to Dr. Kuthe, who is the first person, I'll say, he is the authority in this rapid prototyping, who brought this technology in central India for the first time in 2005. I remember the day myself and Dr. Kuthe, we went to Kadlur in 2005. Kadlur is the city 200 kilometers away from the Chennai, and which was then known for the worst affected city by tsunami. we have learned that there is one industry which is using the patterns by using rapid prototyping. And to see the technology, we visited that company. And what we found that the company owner told us it was the foundry and they're using 3, 4 some patterns. And company owner told us that they brought those patterns from Germany. And it is very hard for them to procure more patterns because patterns itself are very costly and it takes a lot of time if they want to continue with those patterns. And then we found at that time, means 15 years back, there is a scope in this area. And today also you can find the technology is not that much penetrated as far as industries are concerned. Today's our topic is rapid tooling. Especially I chose this topic as the rapid tooling because this is the third day of this FDP, and in first 2 days must have been told about the basics of rapid prototyping and all that. Very little we'll discuss about rapid prototyping, but focus will on tooling itself. Actually, tooling is the comprehensive term which is applicable to the jigs, fixtures, dies, patterns, and molds which are used in the casting industry or anywhere which is required, just like the plastic industry, injection molding, etc. So rapid prototyping concept can be used for development of this rapid tooling. So let's see what is this. The main contents of our discussion will be conceptualization and methods of representations, solution for today and tomorrow.
Excuse me, sir.
Yes.
Sir, the slide is not moving, sir, please.
This was the first. Now this is the second. It is not moving.
No, sir.
No, sir.
Okay, let me check what about this connectivity.
Please change to PowerPoint presentation mode, sir. PowerPoint.
It is showing that shared. There is only one option, that is stop sharing. So if I stop, it will stop. Again, I'll start.
Sir, they must
Now,
start.
can you see now?
Sir, go to the bottom. There's one icon slideshow.
Yeah. This it is maximized on my screen.
Which is there.
Yeah.
Once you start sharing, sir, there are arrows for forward and backward also, and after that stop sharing. So you have to click on that, sir, for moving your slides. Can you see them, sir?
Yes, that I can see.
Yes, with the help
sir,
of
otherwise,
those.
press F5, sir. F5 is the full view, sir.
F5, okay. That
F5,
is there.
full vision.
Yes, sir.
Okay. It is doing nothing with F5. No, that is not the problem. Maximizing and all that. What screen you can see right now?
Agenda.
That you can see?
Yes, sir.
Okay. And now screen is maximized. Now can you not? I'm just changing, but can you not see second agenda? Can you see? Then it's okay.
Yes, sir.
We are on agenda only.
Yes,
can you see agenda? Okay, fine.
Yes.
So contents. Oh, okay, that is the second slide, and we were there only. So contents are conceptualization and methods of representations, then solution for today and tomorrow, application areas of rapid prototyping, RP application for development of rapid tooling, challenges of rapid prototyping, and conclusion. Now, can you see the next third one, conceptualization in design?
Still to come, sir. No, we are only able to see the agenda part.
I don't know why it is happening then. So agenda and clicking next. Still not, you got?
No, sir, not yet.
Okay. Now this way. No?
No, sir.
What was the problem then? If you could see the second slide.
Sir, if you can open the chat window,
Okay.
one of our participants has shown how it is, how we are able to view it. Can you please open the chat window to
Yeah,
see?
it is open now.
Yes, sir. So this is the way we are able to view your slides.
There should not be any show background which should even set.
So if you can go to the right bottom,
Okay.
can you go to the right bottom? Right
Yes.
bottom.
Yes.
There are 3 keys and then 100% is given, sir. Can you see those 3 keys? 1, 2, 3, 3 keys. Can you see, sir?
Right bottom.
Right bottom, sir. Right bottom.
No, here there is some download mobile app or some at bottom there are the participants icons.
No, sir. In your own slideshow, in your own this thing, in your own slideshow, I'm asking.
Yeah, this is the maximization.
Yes, sir. Yes, sir. This one. Click it, sir. Please click on that. Please click on that, sir.
Yes, this was there. Can you see?
We can see difference in conceptual model and mental model.
Okay. Can you see now?
Yes, sir. Yes, sir.
Okay, fine. Now conceptualization in design.
No.
Conceptualization in design, no.
No. We can see difference in conceptual model and mental model. Is this a chair? That's a question you put. Is this a chair?
Okay, means the something lag is there on my system. There is some different slide and okay.
Now it's visible. It's visible, sir. It's visible.
Okay, will it work for you? 100%.
Yes,
I'll maximize.
It's visible now.
Okay.
Sir.
Conceptualization.
Yeah. Please, anybody can help. Yeah.
Sir, there is a slideshow on top menu bar, sir.
Top menu bar.
Yes, sir.
Yes.
Sir, please click on that. Yes, sir. The first tab, please click.
From
please
beginning.
Click the
first, no?
From
okay.
Yes, sir.
Yes, sir.
Now, is it changed
in the
to
mode of slideshow, sir?
No, is it a agenda showing?
Sir,
Conceptualization in
next
design.
one is the from current slide.
Yes, it is showing conceptualization in design.
Design. Okay.
Sir, please click this. Sir, please click on that.
So conceptualization in design, can you see?
Yes, sir. Yes, sir.
Yes, sir.
Okay.
It's not on the presentation mode.
It is not on presentation mode.
Yes, sir.
No, sir. It is not
sir,
on
please,
the presentation mode.
Sir, please, the second slide, the from current slide. Please
Sir,
click
from
on
the
that.
current slide, please click on that. Please click on that. From second slide.
Okay.
Yes, sir. From current slide. You just click it and we'll be able to see, sir.
I click
From current slide.
already.
That's
I already clicked.
Only click, sir.
Okay. You've already clicked, but
yeah.
But we are able to see it on your what you have shared.
Oh.
Sir.
Next slide. Yes, please. Yes.
Sorry. You only put the cursor on that. Please click on that.
From current slide, no?
Yes, sir.
Yeah. I click this. Now this is this.
No, sir. What he's saying, you just go to the slideshow and the second one you click on that, sir. Please move. Click it. Just click it.
Mouse. Please click on that, sir.
Yeah, I click it. Now it is maximized. On my screen, it is maximized now.
but we are unable to see that, sir.
Sir, we are not able.
Oh. So what can be done?
Nothing, sir. Please continue with this. No issues,
Continue,
sir.
sir.
Do F5. F5.
F5 is doing nothing. Control F5 is doing nothing. This is the Microsoft window which I can see, and then I have started my this presentation, and this is the third slide I wanted to share here. Here there are options, that is cancel control and stop presentation. Shall I stop once and again start?
No, sir. Now it was visible completely.
It's
Right.
no
It's visible
issues,
now,
sir.
sir.
You continue.
Continue
You
with
can
this.
continue. Yes, sir. No issues. Not at all.
Okay. So please, you will have to bear with this. Okay. Fine. We'll continue with this then. No problem. This was the agenda actually, and conceptualization in design. Actually, there is the problem always in conceptualization of the ideas. Ideally, user's mental model should be compatible with the designer's conceptual model. Now, there are two persons, one who wants design in industry, and there is other person who is the designer. And one has to communicate the idea, and other has to pursue that idea. And if the ideas are exchanged exactly 100%, then there will be definitely no problem. But it won't happen actually. Now, what is this difference? For example, any person wants to make a chair, and he has given the order that he want such a chair that there will be a comfort. He want comfortable chair. Now, comfort is the relative term, and you cannot exactly define what is mean by the comfort. The comfort for say 5-year boy is different. Comfort for 70-year person is different. And the person to whom we have ordered that the comfortable chair he wants, he has designed this. Now, will you call, is this a chair? Somebody will say yes. Somebody will say no, it is not the chair. It is the bed. And likewise, you may get various answers for that. So there is always the difference between the conceptual models and mental models. In somebody's head, the idea will be different, and communicated idea will be different, and manufactured will be third, just like here. What shape has the right functionality? Actually, there is the superimposition of the images, and now I'll have to show all this one after the other. Otherwise, if I maximize, can you see once again? Just tell me, can you see? I have maximized. Can you see this?
Yes, sir. We can see. No issues, sir.
The picture, nice.
Yes, we can see, sir. What shape has the right functionality?
Functionality, and
yes.
What are the images?
Figures are there. One old man with beards, and the other is razor.
Yeah, very correct. Laser. Okay.
Razor.
Razor. So that is that picture changed now? No. Okay, fine. So here there are various pictures you can see. This second, this third, this fourth, and this first. So what shape has the right functionality? Some 2000 years back, if you would have been asked this question, then this must have been the answer, that this shape can be used to show to the beard person. But some say 100 years back, this must be the answer, that this is comfortable. Some 25 years or 50 years back, this will be the answer. Can you see various pictures now, one or the other?
Yes, sir. Yes, sir.
Yeah. Okay. And some 15 years back, this was the answer. But now this is the answer. So these are the superimposed pictures. So this was the just to explain that there is the how when you have some concept in your mind and when you communicate to other, how the perception changes. So that was the reason behind this. Now you can have trial and error for the razor which have been designed, the spets, the shapes, their say number of blades using in single razor and all that. But when there is the nuclear power plant, then trial and error is some risky. You cannot go for trial and errors. Whatever the design you want, that should be the perfect one. If there is a space shuttle, any spacecraft is launched by any organization, then there cannot be the trial and error method adopted. Now, what will happen if you take the trial and error? Then something will go wrong, and one day that nuclear power plant will blast away. So you cannot take risk in all the cases when you design the systems or products. Now, conceptualization is the biggest problem. So as far as the industrial products are concerned, we learn the engineering graphics because we engineer that product. The dimensions are known, how to measure those, the surfaces are known, but there are some geometry which cannot be measured by any means. No scale is used, no other say dimension measuring device can be used, maybe laser technology, maybe photo using light, some technology. That is not possible. Secondly, can you conceptualize this? And if at all you conceptualize this, you cannot communicate to the other person. That is not possible. That this is the product in my mind and I want it to be fabricated. Neither verbally you can convey this idea, nor on the paper you can sketch it, because what is the surface and what is the contour and what are the overlapping and what is the exact shape and interferences or all that. So that cannot be conveyed. You cannot also design this with the help of computer, because it is necessary that you must be the master in computer. You must be the master in CAD software. So it won't happen generally. Everybody is not perfect in every thing. Customers are different. The designers are different. The manufacturers are different. So that is the conceptualization. That is the meaning that conceptualization is the biggest problem. Now there are methods of representations. If you want to represent any system, there are various methods. Now the simplest method is that the first one, diagrammatic representation. Very first diagram. Actually, it has this presentation is very beautiful presentation because it has the lot of animations, and we miss actually that animation because I don't know why it is not working. I can run here and I can see, but I cannot say let you see it. So first is the diagrammatic representation. Now, first diagram shows that if you want to represent any mechanical system, then this is the one way that it represents, for example, mechanical element spring, which is fixed at one end and free at other end. And at other end, there is the force applied represented by F. And when you apply the force to the spring, since that end is free, it will be displaced by amount X. And K is the stiffness. So there is no need to explain to the mechanical engineer once you draw this. So you'll understand that this is the spring that is fixed at one end, it is the free at one end, and where to apply the force, what force will do, what is the role of K and what is X. And that diagram, that concept, that mechanical spring can also be represented with the help of mathematical model. That is force F, that is input, which is equal to function of X. That is as one changes, the other will change. It should be opposite here. Not F is function of X. It is X is the function of F. Means when you X will change if you change the F, or F is equal to K into X, you will get, for example, force is equal to constant K, and X is the displacement. X is the output and F is the input, and K is the stiffness factor. You can also represent the spring with the help of some block diagram, as called as there are three blocks, one input block, other is output block, and one central block is some transformation goes there, or some mathematical transformation you can have there, which will establish or which will represent the relationship between input and output, how input is related with the output. And then there is the graphical method that X is one node, F is other node, and I'm using this terminology being the person from control system, and 1 by K is gain of that say branch, you can say, and one feedback is also shown there. Other graph shows that is the relationship between the X and F. F is again input. As you will increase the force, then X will increase, and you may get linear graph, non-linear graph, etc. That depends upon what is the value of that stiffness factor and all that. And next way of representing the model is physical model. So physical model, but always it is not possible to represent the physical model. If you want to build some factory, it is not possible, or if you want to build some machine, it is not possible to represent that machine, or have some physical model with the of that machine. But it is one way of representation, and model can be of any model: paper model, clay model, thermocol model, you can have ceramic model, and plastic model, and so many. That is the physical model. This is the one way of representing. And then this very popular technology, that is the computer technology. And computer miracles you can see every now and then. And the last century and this century, this is the century of say computers, because when ENIAC was invented, when it was the first computer which was used in the educational institutions at University of Pennsylvania. The first you can say computing machine, that is analytical engine, which was invented in 1823 by Charles Babbage. And computer technology actually started from that. And in 1941, the first say computer was used by military organizations. So since then, the computer technology is doing miracles. Every now and then, the computing speed, the memory sizes, the display storages, the display resolutions, and everything. Now the speed of communication using higher and higher processors are using. So computer model, that is a simulation we can have. Now these are all say visual simulations which are developed, designed by using some graphics simulation packages and all that, and they can work. They are actually unfortunate here. Now limitations of this CAD/CAM is that despite substantial research in CAD/CAM technology, there is a gap between CAD and CAM in following aspects. Actually, in 1952, the first CNC came when NC was demonstrated at MIT, USA. And the first time this CAD was demonstrated in 1960 at again MIT, when that sketchpad was used for computer graphics. The CAM technology, that is computer, the CNC machines, and the CAM technology went growing on, and CAD technology went growing on. They developed separately CAD and CAM, and later both merge in as the CAD CAM technology. And after emerging this CAD CAM technology, next are the transfer lines, then robotics, and then came CIM. And today people are talking about this industry 4.0 and all that. And the concept is there, that is the factories of futures. AI and machine learning are the hot issues of today. But despite all this research in this CAD CAM technology, the limitation of CAD CAM technology is that rapid creation of 3D models and prototypes are the limitation. It is not possible as far as this rapid word is concerned. And then cost effective production of tooling for the industries. These are the problems. Now, what is prototype? So prototype is usually a physical model. Here, the first this small diagram which represents for this physical model. That is very small, say, there is one product which has the lead and all that, and you can use it on your dining table. And this was fabricated with a 3D printer that I have in my laboratory. Then second is full size or to the scale prototype you can have. Second is example of one bearing that which fabricated. You can fabricate the object to the scale, or say the percentage of it, that is the half or say double size and like that. Then fully or partially functional. Third diagram shows there is one fan and it has a say DC motor connected, and I can plug in and then it rotates. So it works partially and not fully. So you can obtain the product or a prototype which will work either partially or fully. And then prototype can be working model. The last is a jack fabricated on 3D printer as the prototype. And you can, it is fully functional actually, and it can sustain some load also. If you put some 1 kg load, it will sustain, it will rise it up and all that. And then prototype may be virtual model, that is the simulation. So these are various the requirements of prototype. That is, what exactly is prototype? Now our topic was the rapid tooling, and here you can see rapid technologies are there. The concept at the core is rapid technology. Everybody is talking about rapid. That is rapid prototyping, rapid manufacturing, rapid tooling, and it is the solution for today because it is a very hot issue. If you see the challenges in of future, that was some 2016-17 document published by the USA. They identified this virtual reality and 3D printing as one of the future area. And you can see, you have heard to Dr. Kuthe, and he must talk about some medical applications of this rapid prototyping and bioplotters and all that. And that is the need of today. And this government has also asking for the research proposals for this pandemic, who can give the immediate solution over this pandemic. So they are promoting various schemes and all that. So this is the need of today, and it will be need of the tomorrow. Now, what is rapid in rapid prototyping? So we talk about rapid say technologies, rapid prototyping, rapid tooling. Now, what is rapid? Speed of the machine is rapid. Those who have seen these 3D printers, they will find that it is very slow. It takes hours to build. I'll show you one say component which took 18 hours to build. So speed of machine is rapid? No, the answer is speed of machine is not rapid because it is layer by layer manufacturing and it takes its own time. The X and Y movement of the slides that will be governed by the fixed program. You cannot change even that because material, you have to give the sufficient time to solidify the material. So speed of machine is not in our hand. The speed of tool, since there is no tool, there is no point of speed of the tool because there is no RPM as such. There is no say movement of the tool because there is no tool. There are some dispensing devices or some light devices or laser devices and all that, laser gun you can say. Whether technology is rapid, yes, here we can think about something, that is whether we'll see, that is whether technology is rapid or not. And what is technology and is it rapid means what? So if machine is not rapid, then how technology is rapid? So these are some obvious questions about rapid prototyping. Now, what happens in conventional manufacturing? You see the upper diagram, this that is concept, and there is the long bridge, and then product, and then stage 1, stage 2, stage N1, N-1, and stage N. So what happens in conventional manufacturing approach? There is the, for example, some raw material procurement department, and there is design department, and then some, if it is manufacturing, maybe turning department, maybe teeth cutting department, maybe heat treatment, maybe grinding, maybe some post finishing, maybe some inspection. So there has to be a lot of say shops in the industries or in conventional manufacturing, and product has to grow from one stage to second stage and second stage to third stage, unless and until once first stage is completed you cannot send it to third stage for pre-processing, and you cannot skip the stages. So that is the long process. And what is now the answer for these rapid technologies? What happens in rapid technologies that the intermediate steps are removed. There is no as such say uh, the design is not sent from design to first stage, that is you can say scheduling, and then to second shop, then to third shop. Here from raw material to finished product you will get in rapid technologies, and all the intermediate stages are ignored. So that's why this is the rapid. There is no scheduling required in rapid prototyping. There are no further, that is assembly is not required, and intermediate steps are not required. Only the CAD model is required and you get the finished product in your hand. When to prefer rapid prototyping? So the obvious and simple answers are single unique item or small number of copies needed. Unique items, we have seen those three diagrams in which the objects were such that you cannot have measurement of those objects. You cannot put it on the paper. You cannot give the dimensions. You cannot give what is the curvature and all that. The object is either single because the technology being costly, and a unique item. This you cannot manufacture it by any other method. Then it is preferable rather. And shape of the object is in digital form or computer data form. So it is the basic requirement. Unless and until you don't have some CAD file or digital file format, even this X-ray or MRI or CT scan data, if you have the DICOM file, that DICOM file can be used and can be sent to 3D modeler, which will produce the 3D objects. So data must be in digital form, and then software will take care of the digital form data and it will convert it. And shape is too complex to be generated in any other way. For complex shapes, for simple shapes, there are so many variety of the manufacturing conventional process are available. But for complex, it is very difficult, especially some contours, if somebody wants to manufacture, then the process is tedious. Even by using this plastic molding, it becomes difficult because you have to buy the die for that. You have to order it and you have to buy it, and then 3 months duration will lapse in that, and die will be costly. And if you want to fabricate 5 or 10 components, no, it is not possible. It is advisable for mass production only. Application areas of RP, there are so many applications. Now hardly is the field you cannot use this 3D printing technology. You talk about any say field of engineering, mechanical engineering, electronics engineering, civil engineering, computer engineering, the medical sciences. This technology is using nowadays by anybody, even those who want to develop some products as their hobby. They are also using the desktop modelers. So concept modeling, functional testing, analysis, manufacturing, these are the major. And under each this application, there are several applications. Challenges in existing tooling development and need of rapid tooling. So why actually we are discussing this rapid tooling? What is the need and what is the problem with existing tooling development? Small size sand molds are very difficult to fabricate. If you visit to the sand casting industry, you'll find that the objects of the bigger sizes. You cannot say fabricate their manufacture their small components just like investment casting. That is not possible, and that is because of the limitation of the sand mold. Because sand casting process itself is the coarser method of manufacturing. The perfection in contoured patterns is always the problem. Now, conventionally in sandcast industries, the patterns are of either metal or of wood. And when the wood patterns are used, that depends upon the wood worker and he develops the patterns and all that. So perfection in contouring or contoured patterns is a difficulty. Then wooden patterns are dimensionally unstable and metal patterns require finishing time and cost. So wooden patterns are dimensionally unstable because it is sensitive to heat, sensitive to water, and they will sometimes there will be the bulging, and sometimes cracks will be developed in the wooden patterns, and metal patterns will be very heavy, and a lot of time and cost will be involved in fabricating those because it requires finishing, especially the inner part finishing when it is required. It is the tedious job, and accuracy also becomes difficult. Then cores and core prints are separately prepared and assembled. So in conventional practices, cores and core prints are to be separately prepared and separately assembled and positioned at proper places and all that. Then lead time for producing patterns is considerably high. Once you give the order and it takes long time to get the patterns ready. This is the difficulty with conventional pattern making processes. And metal patterns are heavy and wooden patterns being delicate, both required to be handled carefully. One is very heavy. The big patterns cannot be manually handled, and these wooden patterns are delicate. One cannot stack it anywhere because it is very sensitive, say for moisture and all that. So these are the difficulties with existing tooling development practices. Rapid tooling. Basically, this rapid tooling refers to the mold cavities that are either directly or indirectly fabricated using rapid prototyping techniques. So two way we can say fabricate this, that is either direct or indirect way. So we'll just see what is that. And you can have soft tooling and hard tooling. Hard tooling means the tooling made up of these say metal particularly, in which you can pour the software matter and all that, or you can have some sand molds. And soft tooling means production of these toolings, that is flexible toolings. And hard tooling patterns are fabricated by machining the tool steel or aluminum into negative shape of desired components. Scope for this rapid tooling, where these rapid toolings are possible or you can use, because there is need to technology transfer. These concepts are either in the books or the 3D printer fabricators, they are appealing to the industries, but concept has yet not that much penetrated, that much reach extensively in the industries. So there is a lot of scope in sand casting industry, then investment casting industry for plastic molding applications, and as the end product, we can use this rapid tooling. Directly, you can use RP fabricated tooling as the end product. Why to choose rapid prototyping for rapid tooling? So RP fabrication process is basically automated process. Now, how it is automated process? Commercially available 3D printers are there, which only accept the program, computer program, and there is hardly any intervention of human being, because the material is loaded automatically, the temperatures are set automatically, the tool path generations are automatical, the dispensing will be automatical, everything will be automatic in this. The process, RP fabrication process itself is automated. And where from it will get the instructions? It will get instructions from pre-processing software. And pre-processing software is to be the part of that modeler itself. It comes with, software comes with a 3D printer. And what that software accepts, it accepts only the STL file. It recognizes only the STL file. And that STL file we get from the CAD model. So once CAD model is built of a desired product, then you can save that data as the STL, and that STL can be exported to the pre-processing software that comes with the 3D modeler, and then 3D modeler do its work, and it delivers you the finished product. So human intervention is just to load the material, and it is also not needed that every time you require to load the material, there is to be the stacks and all that, and machine will take material from the stack and it will fabricate it, and it will just deliver the product, and it won't also require or hardly any post finishing is required. So in that sense, RP fabrication process is automated. Then fabricate intricate and small parts. So this is the beauty of these 3D printers. It can fabricate all any kind of intricate geometry. I have manufactured one say object. Those are the perforated balls, the 5 balls, one inside the other. Somewhere I think I have shown. And small parts, the miniature parts, you can fabricate. The teeth fabricated with the help of this FDM. Then substantial reduction in lead time. So this is a very important aspect of this rapid prototyping, because when you give order to some company, some vendor, and it takes some weeks, maybe 4 weeks, maybe 8 weeks, maybe few months also. So that is tremendously reduced. Once you get the solid model or some CAD file, you can just start your fabrication. Eliminating toolings. There is no toolings. You can fabricate tooling with the help of rapid prototyping, but 3D printer don't use any tooling. Eliminates process planning. That we have already seen how it eliminates the number of steps. Then customized products. In especially this biomedical applications, many medical say case studies must have been presented by the experts, how the customized implants are can be developed by using this rapid prototyping technology. and how that is used for the patients, and produces no scrap since the building is the part building is layer by layer. There is hardly any scrap developed. Actually, no scrap is developed. The support materials somewhere can be reused and somewhere cannot be reused, and no assemblage of the parts. Absolutely, the screws, the fasteners, uh, the rivets, everything can be fabricated in one stroke. There is no need to join. Only need of the assembly comes when there is the limitation for the fabrication volume, because modelers used to come in with various capacities. Say for example, I have a modeler which can fabricate say 8 inches by 8 inches by say 6 inches this volume. And if you want to build a bigger say component, then you have to build it in the parts and then only assemble. Otherwise, there is no need to. Otherwise, go for the bigger model. Nowadays, the automobile or say customized automobiles parts they are manufacturing by using this 3D printer technology. Direct and indirect rapid prototype toolings. Now you can use this rapid prototype technology for tooling development as in following ways. That is, basic patterns can be produced using any RP technology. The patterns can be used in foundries to produce, say, molds. Then master patterns can be used, which will develop one more pattern. This RP pattern can be used to develop master pattern, and from master pattern you can develop the molds, sand molds, and then number of thousands of components can be produced. Then mold cavities can be produced by using this rapid prototyping for further use, and dies can be used by using this rapid prototyping. We'll see some examples, of course. Now, steps in rapid tooling development with sand casting method. So these steps are shown here. The data can be acquired either by 3D scanning or from concept or from 2D drawing or from part reverse engineering. If you have the part, then you can reverse engineering it. If you have the concept, you can have drawing 3D model of it, or 3D scan model you can have. And from that you will get the CAD model, and from CAD model will give you the part. And if you want to fabricate that part directly, that can be fabricated by using this 3D modeler. And if you want to have negative of it, either say cavities for it or say molds for it, then you can develop from the part CAD model. So that can be the input, and input will be the STL file, and STL file will be supplied to the modeler, which will deliver you the RP pattern, and that pattern can be used for the sand molding. And sand molding, when you will get the course, you can pour the metal and cast the pattern you can get out of that. Or from this sand mold, you can prepare then master pattern by pouring molten metal. Again, use that master pattern to obtain further sand mold, and those sand mold can be used for getting the finished castings. So this way, there are number of ways you can use this 3D printing technology, RP technology, for development of say toolings. Now, how it is used for pattern making? The sand casting process requires the patterns, and you can use it rapid model. Once you have the drawing, then you can have solid model of it. Here there are the two components. This is the first component, the circular one, and this is the second component. For these second components, there are the two drawings and the solid models are obtained for these two components, and these are the patterns. You can see these are the solid models of first component, and this is solid model of the second component, and these are the conventional patterns which are used in the industries for the first component, and these are the patterns used for the in industries for the second component. These are the metal patterns which are already in use and which I studied actually. Then for similar components, these are the wooden patterns for component 1. These are the wooden patterns for component 2. The dimensions are equal, the curvatures are equal, and these are the fabricated, say, ABS plastics. ABS stands for acrylonitrile butadiene styrene plastic. It is the grade of plastic, and those patterns are fabricated. This these two images, this is the front, say, top side, and this is the bottom side of the same pattern. It took 18 hours. This is the solid. Layer resolution is 0.330 mm, and then interior style is solid. It is a heavy one. It can sustain a blow also. If you throw it, nothing will happen to it. The material is very tough, this ABS plastic. And the support style, support which are used, that was the sparse or opaque, you can say. So these are the ABS patterns developed, and this is for the second component. Now, when the testing was done, these are the green sand molds. That is the cope and drag part of this. You can see both the components are shown here, and this is the other side, drag part of both the components, which are obtained from ABS patterns. Means instead of a metal pattern and instead of wooden pattern, we can very comfortably use the plastic patterns, the ABS patterns in this casting industries. And also the surface finish here obtained of the mold cavities can be seen through these images. Then after pouring the metal in the sand molds which are obtained by using the ABS plastic patterns, here there are some examples of the castings of both the components, the top side and this bottom side, and this top side of the first component, top side of the second component. And finishing is better than both the cases in this case. And this is the reason is that why we get better finishing by using these plastic patterns as compared to the wood.